This text describes a series of tasks performed by a code snippet. 1. Checking versions. The snippet validates that the Python version is 3.5 or higher, scikit-learn version is 0.20 or higher, and TensorFlow version is 2.0 or higher. These checks are essential for ensuring the code runs smoothly with the necessary dependencies. 2. Random seed setup. It sets the random seed to 42 using NumPy to ensure reproducibility when generating random numbers in the code. 3. Matplotlib settings. Default font sizes for labels and ticks in Matplotlib plots are configured to adjust the visual appearance of the plots. 4. File paths. The snippet sets up the root directory, chapter ID, and image path for saving generated figures. It also creates an image directory if it does not exist. 5. Save figure function. A function named save_fig is defined, which takes the figure ID, layout options, file extension, and resolution as parameters. This function saves the figure as an image file at the specified location and in the specified format. In summary, this code snippet establishes the necessary environment and utilities for working with machine learning models, creating visualizations, and efficiently saving outputs. It standardizes configurations and ensures that the required library versions are available for the code to execute correctly. This snippet demonstrates how the Perceptron algorithm is utilized to train a binary classifier on the iris dataset. 1. The iris dataset is loaded using the load_iris function from scikit-learn. 2. Only the petal length and petal width features are selected from the dataset as the input data x3. Target labels y are created by converting target values of 0, setosa, in the iris dataset to integer format. 4. A perceptron model is created with specified hyperparameters such as max_iter, tal, and random_state. 5. The perceptron model is trained on the input data x and target labels y using the fit method. 6. The trained model is then used to predict the class of a new data point, 2, 0.5, by calling the predict method. This code provides a simple example of performing binary classification with the perceptron algorithm. The perceptron algorithm functions as a basic linear classifier that determines weights for each feature to distinguish classes in the dataset. By training the perceptron model on the iris dataset, the goal is to predict whether a flower is a setosa or not based on its petal length and petal width. This example serves as an illustration of training and using a machine learning model for classification tasks. The predicted output of a machine learning model is commonly referred to as y_pred. This output is generated when the model is given a set of input data. After training on a dataset, the model can be used to make predictions on new, unseen data by passing it through the model. The predicted values from this new data are typically stored in a variable named y_pred. Having these predicted values is crucial for assessing the model's performance. They are compared to the actual target values to determine how well the model can generalize to new data and make accurate predictions. This comparison is essential for evaluating accuracy, precision, recall, and other metrics of the model. It helps in understanding the model's performance and identifying any necessary adjustments to enhance its predictive capabilities. This segment visualizes a linear classification model's decision boundary on a dataset. The process involves calculating coefficients a and b for the decision boundary equation, setting plot boundaries, generating a meshgrid for the plot area, reshaping the meshgrid for a new feature matrix x_new, predicting class labels using a trained perceptron model, reshaping predicted labels, plotting dataset points and decision boundary line, filling regions with different colors for classes, labeling the plot, adjusting plot axes, and saving the plot as an image file. This visualization helps assess the model's performance in class separation and understand its decision boundary. Three functions are defined in this text: sigmoid, ReLU, and derivative. The sigmoid function calculates the sigmoid activation function for a given input z. The ReLU function implements the rectified linear unit, ReLU activation function. The derivative function is a general-purpose function that calculates the derivative of another function at a specific input value z. The sigmoid function computes the commonly used sigmoid function in neural networks to introduce non-linearity to the model. The ReLU function returns the maximum of 0 and the input z, introducing non-linearity while remaining computationally efficient. The derivative function approximates the derivative of a function f at a specific point z using the definition of the derivative, which is helpful when the derivative is not easily available or hard to compute analytically. These functions are crucial in machine learning, particularly in the development and training of neural networks. Activation functions such as sigmoid and ReLU are important for introducing non-linearity to models, while the derivative function can aid in optimization algorithms like gradient descent for efficiently updating model parameters. This visualization showcases various activation functions and their derivatives in two subplots for comparison. Activation functions are integral to neural networks as they introduce non-linearity, allowing them to grasp intricate patterns. In the first subplot, left side, the functions plotted over the range -5 to 5 are 1. Step function, 2. Sigmoid function, 3. Hyperbolic tangent, tanh function, 4. Rectified linear unit, ReLU function. Each function is depicted with a unique color and line style for clarity, aiding in the comparison of their behaviors within the specified range. In the second subplot, right side, the derivatives of the corresponding activation functions are displayed. Derivatives are crucial for training neural networks using methods like backpropagation that depend on gradients. Understanding these derivatives helps in optimizing the learning process and preventing issues like vanishing or exploding gradients. This visualization offers a graphical representation of diverse activation functions and their derivatives, enhancing comprehension of how they influence a neural network's performance during training and inference. Two functions are defined here. 1. Heaviside, z. This function calculates the heaviside step function for a numeric input z. It returns 0 if z is less than 0 and 1 if z is greater than or equal to 0. The output data type matches the input using the astype method. 2. MLP_XOR, x1, x2, activation. This function implements a multi-layer perceptron, MLP, to compute the exclusive OR, XOR, logic function. It takes x1 and x2 as inputs and uses an activation function, defaulting to the heaviside step function. The function transforms the inputs and applies activation functions to compute the XOR operation. The code serves the following purposes. 1. Heaviside function asterisk. This function is useful for thresholding and generating binary outputs in neural networks and mathematical models. It adds non-linearity and simplifies computations. 2. MLP for XOR asterisk. The XOR operation is not linearly separable, requiring a multi-layer perceptron, MLP, due to its non-linearity. By using appropriate activation functions, the MLP in the code tackles the XOR problem effectively. In essence, this code snippet illustrates the use of activation functions and fundamental neural network principles to address a nonlinear problem, XOR, using Python functions. This visualization compares the outputs of a multi-layer perceptron, MLP, model with different activation functions, heaviside and sigmoid, for the XOR logic gate. 1. Two sets of values, x1s and x2s, are generated to create a grid of points, x1, x2, for the MLP model inputs using NP linspace and NP meshgrid. 2. The MLP_XOR function is invoked twice with x1 and x2 inputs using different activation functions, Heaviside and Sigmoid, storing the outputs in Z1 and Z2 respectively. 3. A matplotlib figure with two subplots is created. Each subplot includes decision boundaries plotted using PLT, contour from the MLP model. Training points 0, 0, and 1, 1, marked with green squares, and 0, 1, and 1, 0, marked as yellow triangles using PLT, plot. Title specifying the activation function used. Display of grid lines with PLT, grid in the background. This code visually demonstrates how an MLP model behaves with various activation functions when trained on the XOR problem. The decision boundaries on the input grid showcase how the model separates XOR classes based on different activation functions. Visualization aids in understanding the influence of activation functions on the model's behavior and performance. This text discusses the use of TensorFlow library and the Keras API. TensorFlow is a machine learning library that is used for creating and training deep learning models. Keras is a neural networks API that can be integrated with TensorFlow. By incorporating TensorFlow and Keras, users can leverage their functionalities to efficiently develop, train, and evaluate deep learning models. TensorFlow serves as a powerful engine for numerical computation and enables the construction of intricate neural network architectures, while Keras simplifies the process of building neural networks with its user-friendly and concise interface. In essence, by utilizing TensorFlow and Keras, users can create an environment for working with deep learning models. These tools are widely embraced in the machine learning and deep learning community for their features, adaptability, and performance. Retrieving the version of TensorFlow, TF, currently installed in the Python environment can be done by accessing the attribute __version __ of the TensorFlow module. Understanding the version of TensorFlow being used is vital as various versions may offer differing features, capabilities, or bug fixes. It also aids in ensuring compatibility with other libraries or packages that may have specific TensorFlow version requirements. This knowledge is essential for troubleshooting issues, seeking assistance in forums, and ensuring the seamless operation of TensorFlow-based applications. Checking the version of the Keras library installed in the Python environment is essential for compatibility and utilizing specific features provided in that version. It does not manipulate data but helps in managing dependencies and ensuring that code runs correctly with the intended Keras version. Different versions of Keras may offer varying functionalities, capabilities, and bug fixes, emphasizing the importance of knowing the installed version for developers. This text discusses the process of importing and loading the Fashion MNIST dataset from the Keras library. The dataset is divided into training and test sets, denoted as x_train_full, y_train_full, x_test, and y_test. This division is crucial for training machine learning models, with the training set used for model training and the test set for evaluating its performance on new data. Fashion MNIST comprises grayscale images of clothes with 28 by 28 pixel dimensions. The labels, Y values, represent 10 clothing categories. The input data, x_train_full and x_test, consists of pixel values from 0 to 255, indicating pixel intensity. By leveraging this process, users can access and use the Fashion MNIST dataset for training and testing machine learning models, especially those focused on image classification. This approach simplifies working with this dataset for various machine learning tasks. This text examines the structure of the variable x_train_full, typically used as the training dataset in a machine learning model. The result of this examination reveals details about the dataset's dimensions, specifically the number of rows, samples, and columns, features. For example, if x_train_full shape returns 60,000, it indicates the presence of 60,000 samples in the dataset. Understanding the dataset's shape is vital in working with machine learning models, as it assists in correctly setting up the models and ensuring data compatibility before training. Being aware of the dataset's shape and size is crucial for debugging errors related to data dimension discrepancies and for making well-informed decisions in preprocessing, model selection, and evaluation. tegsetunun x_train_full bayelui dietio tibial waganan yangdulo seangdubnida, dtype bayel yosawi dietio tibial bonwanabnida. Unsigned int 8-bit, bayel yosoga 8-biteu buho eobisnun jungsolul natanabanida. Ulinian kodeliusal seangheyo dietio hyungsigul ihihego olbaliuj chulahagi yhi ilial seanghabnida. Ditawi dietio tibial pagamian detaileul dalal titae balsangal su isnun mungina yegichi moshan dongjegul bengjihego olbaliuj chulahal su ishabnida. Ditawi dietio tibial ihihanian geosun ditawi gabsul jayungwaghage hisogago hawalanghanian de mayu jungyohabnida. This text discusses preparing a dataset for training a machine learning model. 1. The dataset is divided into a training set, x_train, and a validation set, x_valid, with the first 5,000 samples designated for validation and the rest for training. The division by 255.0 suggests feature scaling to normalize values between 0 and 1. 2. The target labels, y_train_full, are also split into y_valid and y_train following the same split as the features. 3. The test dataset, x_test, undergoes feature scaling by dividing all values by 255.0 to ensure consistency with the training data. Feature scaling and dataset splitting are crucial in machine learning. Feature scaling normalizes data, aiding convergence and improving algorithm performance. Dataset splitting provides insights into model performance on unseen data and helps prevent overfitting by tuning hyperparameters on the validation set. In the context of machine learning and data analysis, y_train refers to the labels or target variable in a dataset. In supervised learning, datasets consist of features, input data, and labels, output data, with y_train specifically representing the labeled part of the training dataset. This component denotes the known outcomes or classifications corresponding to the input data found in x_train. The utilization of y_train is essential as it allows machine learning models to be trained using labeled data to identify patterns and generate predictions. By supplying the accurate labels during the training process, the model can adjust its parameters to minimize errors between the predicted outputs and the actual labels, enhancing its ability to provide precise predictions for new, unseen data. In essence, y_train plays a critical role in training and assessing machine learning models by offering the actual values for the corresponding input data. This facilitates the model in learning from the training data and extending its predictions to new, previously unseen instances. This snippet displays an image from the training dataset. The first print statement shows the dimensions of the entire training dataset. The second print statement displays the dimensions of the first image in the training dataset, which is 28 by 28 pixels. PLT im show x_train 0 cmap equals binary displays the first image in the training dataset as a grayscale image using the binary color map for black and white. PLT axis off removes the axes in the image plot for a cleaner visualization. Finally, PLT show displays the image. This code is crucial for visualizing data and understanding the image data structure. It aids in verifying data integrity for training machine learning models and facilitates exploration and understanding of the data before further processing or analysis. In the context of machine learning and data science, y_train is a variable that typically represents the target variable or labels in a dataset. In supervised learning, we work with input data, x, and corresponding output data, y, where y_train is specifically the output data used for training machine learning models. This variable provides the labels used during training to help the model learn the relationship between input features and output labels. The role of y_train in machine learning is crucial for training a model to accurately predict output labels based on input features. By supplying the correct answers, labels, during training, the model adjusts its parameters to minimize prediction errors and enhance its performance on unseen data. Properly splitting the dataset into features, x, and labels, y, is essential for training a machine learning model and assessing its performance. The y_train variable contains the true labels that the model aims to predict, making it a vital component of the training process. A list called class_names is created, containing strings that represent various fashion items. These strings correspond to specific class labels in a fashion-related classification problem. This list can help map numeric class labels to string representations for model training or evaluation. It's especially beneficial in image classification, where associating class names with numeric labels aids in interpretation and visualization. This snippet indexes into an array or list called class_names using the value stored at the first index of another array, y_train. In this scenario, y_train likely contains the labels or target values of a machine learning dataset, while class_names is an array storing the corresponding class names or labels. By accessing the value at the first index of y_train as an index for class_names, the code fetches the class name associated with the first label in y_train. This technique is commonly employed in machine learning applications to translate numerical class labels into human-readable class names for easier result interpretation or visualization. It facilitates the linking of numeric values to their corresponding textual representations. The x_valid shape function retrieves the shape of the x_valid array or matrix. It does not manipulate the elements of the array but provides information about its dimensions. The shape is presented as a tuple with the number of rows followed by the number of columns, e.g., rows, columns. This function is valuable in data analysis and machine learning tasks where comprehending the data's dimensions is essential for processing and modeling. By determining the shape, we can understand the data's structure, adjust it as needed, and ensure it is compatible with different algorithms and operations. The x_test shape is a commonly used term in the field of machine learning. It is used to display the structure of the data stored in the variable x_test, which typically contains a dataset or a NumPy array with features for testing a machine learning model. The shape attribute of x_test returns a tuple that shows the array's dimensions. The first element indicates the number of rows or samples, while the second element represents the number of columns or features in the dataset. Understanding the data's shape is crucial for various tasks. For example, it is important to verify that the input data has the correct dimensions before feeding it into a machine learning model. Knowing the data's shape allows data scientists and machine learning engineers to preprocess and manipulate the data effectively for training and validating machine learning models. Furthermore, checking the data's shape helps in identifying issues such as mismatched dimensions that could cause errors during the modeling process. Therefore, utilizing x_test shape offers valuable insights into the test data's structure, which helps in appropriately managing and processing data in the machine learning workflow. This text describes a script utilizing the matplotlib library to plot a grid of images from the Fashion MNIST dataset. It specifies the number of rows and columns of images from the training set to display. The variables n_rows and n_calls determine the grid size for plotting. The script generates a figure of a specific size based on the rows and columns provided. It then loops through each cell in the grid to plot an image from the x_train dataset using a binary color map, removes axis labels, and sets titles based on the corresponding class names from the y_train labels. Once all images are plotted, the script adjusts the spacing between subplots with subplots_adjust. Finally, it saves the plot as an image file named fashion_mnist_plot, and displays the plot. This script is beneficial for visualizing multiple images in a grid layout, like in this instance to view image data from the Fashion MNIST dataset. It aids in understanding the dataset and identifying patterns in the data, which is valuable for tasks like image classification where visual data inspection is critical for model development. A neural network model is being created using the Keras library in Python. 1. The sequential function is used to create a sequential neural network model where layers are added one after the other. 2. The flatten layer reshapes the 2D image data, 28 by 28 pixels, into a 1D array, 784 pixels, as the first layer of the model. 3. Dense layers are fully connected layers in the neural network. The first dense layer contains 300 neurons with ReLU activation function to capture nonlinear patterns in the data. 4. The second dense layer contains 100 neurons with ReLU activation function. 5. The last dense layer contains 10 neurons, as there are 10 classes in the dataset, with softmax activation function for multi-class classification tasks. It outputs a probability distribution over the 10 classes. Building a neural network model is essential for tasks like image classification, where the model needs to learn complex patterns from input data and make predictions. The sequential model simplifies adding layers and specifying activation functions, helping introduce non-linearity for better learning and generalization on unseen data. In a machine learning application using Keras with TensorFlow backend, the following functions are utilized. 1. Keras backend clear_session ***. This function clears the Keras session, removing the graph and freeing memory. It ensures that each model starts with a clean session, avoiding clutter from previous models and potential memory leaks. 2. NP random seed 42 ***, sets the seed for the NumPy random number generator, enabling reproducibility of random results in subsequent runs. This is beneficial for debugging and ensuring consistent outcomes in data preprocessing and model training. 3. TF random.set_seed 42 sets the seed for the TensorFlow random number generator, ensuring reproducibility in TensorFlow operations like weight initialization and dropout. By implementing these functions, reproducibility in machine learning experiments is maintained by setting seeds for random number generators in both NumPy and TensorFlow. This practice is vital for debugging, result sharing, and consistency in data processing and model training outcomes across different code executions. This text describes the creation of a neural network model using the Keras library. Each part of the code is explained as follows. 1. Keras. Models. Sequential. This function is used to create a model that consists of a linear stack of layers. 2. Keras. Layers. Flatten, input_shape equals 28, 28. This layer transforms the input, which is a 28 by 28 array representing an image, into a 1D array containing 784 elements. 3. Keras. Layers. Dense, 300, activation equals ReLU. This layer creates a fully connected layer with 300 neurons and applies the ReLU activation function to its output. 4. Keras. Layers. Dense, 100, activation equals ReLU, another fully connected layer with 100 neurons and ReLU activation function. 5. Keras. Layers. Dense, 10, activation equals softmax. This is the output layer with 10 neurons, for a classification task with 10 classes, and uses the softmax activation function to output probabilities for each class. Neural networks are commonly used for tasks such as image classification, where they are trained to recognize patterns in the data and make predictions based on those patterns. This code establishes the structure of the neural network with input, hidden, and output layers, as well as activation functions to introduce non-linearity and facilitate the learning of complex data patterns. Defining the architecture of a neural network through code is essential as it determines how data passes through the network and how predictions are generated. It allows the specification of layer types, the number of neurons in each layer, and the activation functions employed, all of which are vital for successful learning and accurate predictions. The layers of a neural network model are the foundational components that transform input data into the desired output. By examining the layers of a model, we can investigate or adjust various properties like weights, biases, and activation functions. This ability is crucial for tasks like debugging, refining, or transferring models. Comprehensive knowledge of a model's structure via its layers is vital for evaluating its effectiveness and behavior. The model summary function is commonly utilized in machine learning libraries such as TensorFlow or Keras to offer a brief overview of the neural network model that has been specified. This summary entails details regarding the model's structure, comprising the type of each layer, output shape of each layer, parameter count, and overall parameters in the model. By utilizing model summary, you can swiftly grasp the model architecture and ensure that it has been defined correctly. This aids in debugging and confirming the correct construction of the model before training it with data. This summary proves especially beneficial when handling intricate neural network architectures with numerous layers. This tool is used to create a visual depiction of a Keras model in the form of a flowchart or graph. It illustrates the neural network model's architecture, showcasing the layers, their connections, input, output shapes, and types. By setting show_shapes equals true, the shapes of input and output tensors for each layer are displayed in the visualization. This visualization is valuable for comprehending and troubleshooting intricate neural network models, particularly those with many layers. It offers a clear outline of the model structure, aiding in issue identification, confirming layer configurations, and validating data flow through the network. A visual representation of the model is also beneficial for explaining the architecture to team members or stakeholders, as it is more easily understandable than code alone. In conclusion, using the plot_model function from the Keras library is instrumental in visually representing neural network models for improved comprehension, debugging, and communication. To access a specific layer in a pre-defined model, we can retrieve the second layer and obtain its name. In deep learning models, layers perform unique operations on input data, stacked on top of each other. Understanding the layer's name can aid in debugging, monitoring the training progress, or customizing functionalities that involve interacting with specific layers of the model. To retrieve a layer named hidden 1 from a neural network model specified by model, the code uses the get_layer method provided by the model with the name of the desired layer as an argument. This code is essential for accessing or modifying a particular layer within a neural network model. Referencing layers by name allows tasks such as extracting outputs from intermediate layers, setting layers as trainable, non-trainable, or connecting layers in more complex architectures. This capability provides flexibility and control over the structure and functionality of neural network models. This operation retrieves the weights and biases of a neural network layer named hidden 1 foot and saves them in the variables, weights, and biases, respectively. Extracting these learned parameters from the specified layer is crucial for tasks such as debugging, evaluating model performance, and implementing advanced techniques like transfer learning or fine-tuning pre-trained models. By analyzing these weights and biases, we can understand how the model generates predictions and use this information to optimize and develop the model further. Weights are essential numerical values utilized in machine learning algorithms, primarily in tasks such as classification or regression. These weights serve as parameters that are acquired during the training process of a machine learning model. They are fine-tuned iteratively using the input data and desired output to minimize the error or loss function. In the realm of neural networks, weights signify the potency of connections between neurons across various layers. Their relevance is evident as they get multiplied by input values and then undergo an activation function to yield the neuron's output. Weights play a crucial role in machine learning as they aid the model in making precise predictions by recognizing patterns and correlations within the data. Through the adjustment of weights based on training errors, the model can enhance its performance over time and exhibit effective generalization towards unseen data. The function will provide the structure of the weights array or tensor. The structure of an array or tensor indicates the number of elements in each dimension of the array. For instance, a 2D array would have a shape like rows, columns. Comprehending the structure of arrays or tensors plays a crucial role in data manipulation and mathematical operations within machine learning and data processing. Having a grasp of the data's structure allows you to execute operations accurately and ensures that the dimensions of arrays are compatible for tasks like matrix multiplication, element-wise operations, and data reshaping. Biases in machine learning serve as constant values added to the output of a neuron within a neural network. They play a crucial role in shifting the activation function to the left or right, enhancing the model's ability to align with the data. By incorporating biases, the model gains the capacity to understand intricate functions and generate more precise predictions. In neural networks, biases are essential for enabling the model to discern patterns and connections within the data. Their absence could hinder the model's learning process and its ability to perform effectively on new datasets. By fine-tuning biases throughout the training phase, the model can enhance its predictive accuracy and overall performance. Retrieving the shape of the biases tensor in a neural network model is crucial for comprehending the structure of the network, identifying errors, and troubleshooting bias-related issues. Understanding tensor shapes is essential in deep learning to facilitate the correct data flow within the neural network. This snippet configures a neural network model using TensorFlow in a Python script. Here's an overview of what it does and why it's important. 1. The compile function sets up the model's learning process before training. It defines the loss function, optimizer, and metrics for training. 2. Setting loss equals sparse underscore categorical underscore crossentropy specifies the loss function for multi-class classification tasks with integer target labels. 3. Selecting optimizer equals SGD configures the optimizer as stochastic gradient descent (SGD), a widely used algorithm for updating neural network weights based on calculated gradients to minimize the loss function. 4. Defining metrics equals accuracy sets the evaluation metric to track and display accuracy during training and evaluation, which is commonly used for classification tasks to show the percentage of correctly classified samples. By using this code, we prepare the neural network model by specifying how to measure performance, loss, update weights, optimizer, and track metrics. These configurations are crucial for achieving good training results and effectively evaluating the model's performance. This procedure utilizes the fit method of a machine learning model to train on the x_train and y_train data for 30 epochs. In the process, the model's performance on the validation data, x_valid, y_valid, is assessed to evaluate its generalization capability. The epochs parameter dictates how many times the model will iterate through the training data. Throughout each epoch, the model updates its internal parameters using an optimization algorithm to minimize the loss function on the training data. The fit method plays a crucial role in machine learning by facilitating model training on a specified dataset, adjusting its weights, and enhancing its performance. Monitoring validation data aids in preventing overfitting and offers insights into how the model might fare on unseen data. In programming, the term history often relates to a web browser's browsing history. In this case, params likely denotes parameters within a URL. The specific functionality of history params cannot be conclusively determined without further details about the code or its application environment. In web development, parameters are frequently used to convey information between pages or define how a page should load. This code snippet may be utilized to manage these parameters or monitor browsing history within a web application. The epoch attribute of a history object in deep learning frameworks like TensorFlow or Keras signifies the number of iterations a model has completed on the entire training dataset. Monitoring and printing the epoch allows tracking the progress of model training, indicating the current stage of training and the total completed epochs. This information is crucial for managing the training process, aiding in deciding when to halt training or fine-tune hyperparameters. This snippet retrieves the keys in the history dictionary, utilized in Python interactive mode and Jupyter notebooks to store the output of previously executed commands. By accessing the keys of the history object, you can see the numbers representing the order of commands executed. This is beneficial for tracking and referencing past commands within a Python interactive environment. This snippet uses the Python library pandas to create a dataframe from the history dictionary, which typically contains training, validation metrics during the training of a machine learning model using Keras. The plot function is then used to display the data as a line graph. After that, plt grid true adds a grid to the plot for better readability. The plt.gca.set_ylem 0, 1 command sets the y-axis limits of the plot between 0 and 1. Finally, the save_fig Keras_learning_curves_plot function saves the plot as an image file named Keras_learning_curves_plot in the current directory. Then, plt show displays the plot on the screen. This code is valuable for visualizing the training and validation metrics of a machine learning model during training, aiding in monitoring its progress and performance. The plot offers insights into how these metrics change over epochs and can assist in debugging, optimizing, and fine-tuning the model. This snippet is used to assess the performance of a trained machine learning model on a test dataset. The evaluation process calculates the model's loss and accuracy using the input features x_test and corresponding target labels y_test. The loss value reflects the model's performance, with a lower value indicating better performance. Accuracy represents the ratio of correctly predicted outcomes to the total number of predictions made by the model. By assessing the model on a separate test dataset, we can gauge its ability to generalize and predict on new data. This evaluation is essential for understanding the model's expected real-world performance and for comparing different models. This operation involves the following steps. 1. Selects the first 3 samples from the test dataset, x_test, and stores them in a new variable called x_new. 2. Utilizes a pre-trained model to predict the probabilities of each class for the samples in x_new, storing the predicted probabilities in the variable y_proba. 3. Uses the round function to round the predicted probabilities in y_proba to 2 decimal places. The main objective of this code is to showcase how a pre-trained machine learning model can be employed to generate predictions on new data, specifically x_new, and to acquire the probabilities for each class. By rounding the probabilities to 2 decimal places, the output becomes more readable and easier to work with for interpretation or further analysis. This process aids in comprehending how the model assigns probabilities to different classes and facilitates decision-making based on those probabilities. This is a process to make predictions using a machine learning model. Here is an overview of the steps involved. 1. Utilizing the model. Predict x_new function with a machine learning model to predict outcomes based on the input data x_new. 2. The NP argmax function is employed to determine the indices of the highest values along a specific axis. In this scenario, it is applied to identify the index with the highest predicted probability obtained from the model. Predict method. 3. By specifying axis equals -1, the function operates along the designated axis for argmax. Here, it is set to -1, representing the final axis. This is usual when working with multidimensional arrays. 4. The variable y_pred holds the forecasted class labels by identifying the index with the highest probability along the assigned axis. By implementing this process, we can derive the predicted class labels for the provided input data. These predicted class labels can then be used for subsequent analysis, assessment, or other tasks within a machine learning workflow. This process uses NumPy to associate the predicted class indices, y_pred, with their respective class names. Initially, an array of class names, represented as class_names, is generated. The elements within y_pred are utilized as indices to match and retrieve the corresponding class names from the class_names array. This approach proves beneficial when dealing with a classification model that provides class indices rather than class names. Converting these indices into their human-readable counterparts facilitates improved interpretation or visualization of the outcomes. The primary purpose of this code is to convert the numeric predictions from the model into more understandable class names. A new variable y_new is created to store the first 3 elements of the y_test variable. This is done by slicing the y_test array from the beginning up to, but not including, the element at index 3. This approach can be valuable when you need to extract a subset of data from an array for additional processing or analysis without altering the original dataset. Slicing enables you to focus on a specific part of the data without changing the original array. A figure is created with a specific size of 7.2 by 2.4 inches and populated with subplots containing images from a dataset named x_new. The images are displayed in grayscale, binary, with nearest neighbor interpolation. Class names for each image are shown as titles above the images. The loop goes through each image in x_new, displaying one image per subplot. The space between subplots is adjusted for better readability using the subplots_adjust function. The plot is saved as an image file named Fashion MNIST images_plot and displayed with plt show. This approach is beneficial for visualizing a set of images commonly used in tasks like image classification or analysis, aiding in examining the images and gaining a deeper understanding of the dataset. Saving the plot enables easy sharing or embedding in reports or presentations. This process accomplishes the following tasks. 1. It retrieves the California housing dataset using fetch_California_housing function from sklearn datasets. 2. Divides the dataset into a training set x_train_full, y_train_full, and a test set x_test, y_test using train_test_split function from sklearn model_selection. 3. Further divides the training set into training x_train, y_train, and validation set x_valid, y_valid, using train_test_split, once more. 4. Creates a standard scalar object to standardize the features of the dataset. 5. Standardizes the features x_train, x_valid, x_test by applying the fit_transform method on the training set and transform method on the validation and test sets. Standardizing the features is crucial as it normalizes the data to have a mean of 0 and a variance of 1. Standardization is necessary for various machine learning algorithms like support vector machines, k-nearest neighbors, and neural networks, which require the data to be both centered and uniformly scaled. This preprocessing step enhances the performance and training stability of these algorithms. This text explains how setting the random seed for 2 libraries, NumPy and TensorFlow, helps ensure reproducibility in results for tasks such as machine learning and data analysis. It ensures that the sequence of random numbers generated remains the same each time the code is executed, allowing for consistent and comparable results. This practice is valuable for testing, debugging, sharing code, or reproducing results in the future. This text describes a sequence of tasks performed using the Keras library to build and evaluate a neural network model for regression purposes. 1. A sequential model is created using Keras, comprising layers that process data sequentially. 2. The model includes 2 dense layers. The first layer with 30 neurons using ReLU activation and an input shape determined by x_train, and the second layer with 1 neuron for the output. 3. The model is compiled with mean squared error loss and stochastic gradient descent optimizer set at a learning rate of 1e3. 4. Training occurs on x_train and y_train data for 20 epochs, with performance validation on x_valid and y_valid. 5. Model evaluation is done on the test set x_test and y_test, using mean squared error as the loss metric. 6. Predictions are generated using the trained model on the first 3 samples from x_test. 3. This code streamlines the process of building, training, and assessing a neural network model for regression tasks, aiding in understanding the relationship between input features, x, and target labels, y, to predict outcomes on unseen data. It offers a structured approach to train a basic neural network using Keras, from defining model architecture to evaluating its performance on test data. This text explains the use of the matplotlib library for visualizing and plotting data. Each aspect of the process is detailed as follows. 1. Plotting a graph using the data from the history object, which likely contains training history data of a machine learning model, such as loss and accuracy metrics over time. 2. Adding a grid to the plot to improve its readability. 3. Setting the y-axis limits of the plot between 0 and 1. Commonly used for metrics like accuracy within the range 0, 1. 4. Displaying the plot for the user to view. This code is utilized to visually analyze the model's performance during training. The plot helps in understanding various aspects such as convergence, overfitting, underfitting, etc., by presenting metric changes across epochs. This visual representation aids in adjusting model hyperparameters and enhancing overall performance. y_pred is a commonly used variable name in machine learning to represent the predicted values produced by a model based on input data. These predictions are the model's output after it has been trained on a dataset. In a typical machine learning scenario, there are input features, x, and target values, y, used to train a model. Once the model is trained, it can be used to predict outcomes on new, unseen data, with these predictions being stored in the y_pred variable. Assessing the model's performance requires comparing the predicted values, y_pred, to the actual target values. This evaluation helps determine the model's accuracy and enables adjustments if needed. This is a crucial step in developing and optimizing machine learning models for various applications. Setting the random seed values for NumPy, NP, and TensorFlow (TF) libraries to 42 ensures that the random values generated by these libraries remain consistent each time the code is executed. This is valuable in scenarios such as machine learning experiments or simulations, where reproducing the same results is necessary for debugging or result comparison. By specifying the random seed, we gain control over the randomness in code execution, making it both controlled and reproducible. This level of consistency is particularly important in tasks like model evaluation, hyperparameter tuning, and debugging, as it simplifies the analysis and comparison of results. This text describes the process of creating a neural network model using the Keras library. Here's an overview of each part of the process. 1. Define an input layer with a shape based on the training data. 2. Add a dense layer with 30 neurons and ReLU activation on top of the input layer. 3. Add another dense layer with 30 neurons and ReLU activation on top of the previous layer. 4. Concatenate the input layer with the output of the second hidden layer. 5. Add a final dense layer with one neuron on top of the concatenated layer for regression tasks. 6. Create a Keras model specifying the inputs and outputs of the neural network model. This code is used to design the structure of a neural network model for regression tasks, where input data is processed through multiple hidden layers with activation functions to generate output predictions. Keras simplifies building neural network models by offering pre-built layers and activation functions. In a machine learning context, calling model summary provides a condensed overview of a neural network model's structure. common in Python with libraries like TensorFlow or Keras. The summary details each layer's type, output shape, and parameter count. Reviewing the summary allows for a rapid grasp of the neural network's layout and ensures alignment with the planned design. This aids in debugging and resolving model-related problems. Fundamentally, model summary serves as a visual inspection tool for data scientists and machine learning engineers to confirm layer setups, optimize performance, and fine-tune neural network models. To train a machine learning model using the Keras library with TensorFlow backend, standard steps are followed. Here is an overview of each step. 1. Configuring the model for training is done by calling model compile. This step involves specifying the loss function, mean squared error for optimization and defining the optimizer, stochastic gradient descent with a learning rate of 1e3. 2. Training the model using model.fit involves fitting the model to training data x_train and y_train for a set number of epochs, 20 in this example, and validating its performance on validation data x_valid, y_valid during training. 3. Evaluating the model on the test dataset x_test, y_test to assess its performance after training is done using model evaluate. The specified loss function, mean squared error, is used for this evaluation. 4. Once the model is trained and evaluated, model predict is used to predict the output for new data x_new using the trained model. These steps are crucial for training a neural network, assessing its performance, and making predictions on new data. The compile function sets the optimization strategy and loss function, fit trains and evaluate tests the model, and predict generates predictions on unseen data. Setting the seed for both NumPy, imported as NP, and TensorFlow, imported as TF, random number generators ensures the reproducibility of results. A random seed allows us to generate the same random numbers each time the program is run, which is helpful for debugging and result comparison. By setting the seed to a specific value, such as 42 in this case, we guarantee consistent random number generation regardless of how many times the code is executed. This practice improves the predictability and reproducibility of our results, which is essential for research, testing, and debugging machine learning algorithms and models. It ensures that randomness in the program does not impact the results, enabling us to identify and resolve issues more efficiently. This text describes the creation of a neural network model with two input layers. One input layer, called wide_input, has an input shape of 5. While the other input layer, deep_input, has an input shape of 6. The model includes a deep neural network component that takes input from the deep_input layer, processes it through two hidden layers with ReLU activation functions, and then combines this output with the input from the wide_input layer. The combined output then goes into a final dense layer to give a single output value. The purpose of this implementation is to build a more intricate neural network structure capable of handling both wide and deep inputs concurrently. This model design, called a wide and deep model, is particularly beneficial for structured, tabular data that contains complex relationships requiring deep neural network layers for capturing deep patterns, as well as simple linear or low-order interactions that a shallow model can capture well. The wide component, wide_input, retains frequent item memorization, while the deep component, deep_input, learns abstract features for generalization. The concatenated layers enable the model to effectively learn both deep and shallow patterns. This segment involves training a neural network model with two sets of input data. Initially, the model is compiled with mean squared error as the loss function and stochastic gradient descent (SGD) as the optimizer using a specific learning rate. The input data is then divided into x_train_A and x_train_B for training, and similarly for validation and testing. This division allows different parts of the input data to be fed into distinct sections of the neural network for improved feature learning. Subsequently, the model is trained using the fit method by supplying x_train_A, x_train_B, and the target labels y_train for a defined number of epochs. Validation data is included to monitor the model's performance on unseen data. Post-training, the model is assessed on the test data to compute the mean squared error (MSE). Finally, the model generates predictions on new data points x_new_A, x_new_B, and saves the predicted outputs in the variable y_pred. This code structure facilitates the development of intricate neural network architectures that can effectively leverage various parts of the input data for enhanced learning and predictive capabilities. Setting the seed for random number generators in NumPy and TensorFlow libraries ensures that the same random numbers are generated each time the code is executed. This practice is essential for achieving reproducibility in machine learning experiments. By fixing the seed, you can consistently produce the same results for random initializations and operations, enabling effective debugging, validation, and comparison of models and algorithms. This neural network model is created using the Keras library. The process involves defining input layers for wide and deep inputs, creating hidden layers with a ReLU activation function, concatenating the outputs, defining output layers, and finally creating a model with specified input and output layers. This code is used to build a multi-input, multi-output neural network model. This architecture is beneficial when handling various types of input data or when auxiliary outputs are required for regularization or guiding training. By utilizing different input and output layers, complex models can be constructed to simultaneously learn different aspects of the data. This configuration sets up a neural network model for training using the Keras library. Two mean squared error, MSE, loss functions are specified for the model to optimize. Different weights are assigned to each loss, with the first MSE loss being given more importance during optimization. The stochastic gradient descent (SGD) optimizer is configured with a learning rate of 0.001 to update the neural network's weights during training to minimize the specified losses. In summary, this setup prepares a model to be trained using the SGD optimizer with two MSE losses, where the weight of each loss can be adjusted. Customizing loss functions and their weights can be beneficial when optimizing multiple objectives simultaneously and balancing their importance throughout training. This method utilizes the fit function of a machine learning model to train the model using training data and then evaluate its performance on validation data. The model is trained on two input arrays, x_train_A and x_train_B, and two target arrays, y_train, for 20 epochs. In addition, it assesses the model's performance on validation data, which includes two input arrays, x_valid_A and x_valid_B, and two target arrays, y_valid. The objective of this process is to enable the model to recognize patterns within the training data and assess how well it performs on new, unseen data, represented by the validation data. This evaluation helps in determining if the model is overfitting to the training data and how effectively it generalizes to unseen data. Consequently, adjustments can be made to the model's hyperparameters to enhance its performance. This neural network model performs evaluations and predictions. In the evaluate method, The model uses test data x_test_a and x_test_b, along with test labels y_test, to predict outputs and calculate total loss, main loss, and auxiliary loss. These metrics evaluate how well the model performs on the test data. In the predict method, the model uses new data x_new_a and x_new_b to predict outputs stored in y_pred_main and y_pred_aux. These evaluations and predictions are essential for assessing the model's performance, adjusting parameters, and making decisions like modifying hyperparameters or architecture to enhance predictive ability. The custom neural network model named Wide and Deep Model is defined using the Keras framework. This model includes two hidden layers, hidden 1 and hidden 2 of the same size with a specified activation function. It has two output layers, main_output and aux_output, each producing a single numeric output. In the Wide and Deep Model class's call method, the model processes two separate inputs, input_a and input_b. Input_b goes through hidden 1 to hidden 2. Then, the outputs of input_a and hidden 2 are concatenated. The concatenated output is then passed through the main_output layer to generate the main prediction. Additionally, the output of hidden 2 is passed through the aux_output layer to produce an auxiliary prediction. The purpose of creating this wide and deep model is to combine the strengths of shallow and deep learning architectures. This model is ideal for scenarios where the model needs to learn simple patterns from a wide range of features, shallow network, and complex patterns from a smaller set of features, deep network. The architecture of this model allows it to capture intricate relationships in the data and enhance the predictive performance of the model. This workflow involves training a neural network with multiple outputs. Compiling the model involves specifying the loss function, mean squared error, loss weights, 0.9 for main output, 0.1 for auxiliary output, and optimizer, stochastic gradient descent with learning rate 1e3. Using model.fit, to train the model with training data and validate performance using validation data for a specified number of epochs. Using model. Evaluate, to assess the trained model's performance on test data, providing total loss and individual losses for main and auxiliary outputs. Generating predictions with model. Predict, on new data, storing predictions for main and auxiliary outputs separately. This code is crucial for training neural networks with multiple outputs, with customizable loss functions, weights, and optimizers for desired training behavior and output predictions. Setting a random seed for NumPy and TensorFlow libraries ensures that the same sequence of random numbers is generated each time the code is run. This is important for reproducibility, making it easier to replicate and verify results. Random seeds are commonly used in machine learning experiments to control randomness and produce consistent outcomes. NumPy and TensorFlow utilize random number generators in different functionalities, so setting a seed helps to maintain consistency in the randomness generated by these libraries. This text explains the process of creating a neural network model using the Keras library with a TensorFlow backend. 1. The code begins by creating a neural network model using Keras models. Sequential, which generates a linear stack of layers for the model. 2. The first layer, Keras layers. Dense 30 activation equals ReLU input_shape equals 8 adds a fully connected layer with 30 units and a ReLU activation function. It defines the input shape of the data as 8, indicating that the model expects input data with 8 features. 3. The second layer, Keras layers. Dense 30 activation equals ReLU adds another fully connected layer with 30 units and a ReLU activation function. The input shape for this layer is automatically determined based on the previous layer. 4. Finally, Keras layers. Dense 1 adds the output layer with 1 unit, typically used for regression tasks without specifying an activation function. Neural networks comprise interconnected nodes, neurons, across multiple layers that learn to map input data to output data through a training process. Activation functions like ReLU introduce non-linearity to the model, allowing it to capture intricate patterns in the data. This code is essential for constructing a feed-forward neural network, a type of deep learning model used for tasks such as regression or classification. It establishes the network structure and defines how data will flow through the model during training and inference. This text describes the process of training a neural network model. The model is compiled using mean squared error, MSE, as the loss function and stochastic gradient descent, SGD, as the optimizer with a specific learning rate. 1. The model is compiled by specifying MSE as the loss function and SGD as the optimizer with a learning rate of 1e3 using model compile function. 2. The model is then trained for 10 epochs on training data, x_train, y_train, using the fit function. Validation data, x_valid, y_valid, is used to validate the model's performance during training. 3. After training, the model's performance is evaluated on test data, x_test, y_test, using evaluate function with MSE loss function, returning the MSE value. This code is essential for compiling and training the neural network model. Compiling specifies the loss function and optimizer, while training adjusts model parameters to minimize the specified loss. Evaluation provides insights into the model's performance on test data. Following these steps ensures accurate training and assessment of the neural network model. A Keras model can be saved to a file named my_Keras_model H5 in the current directory. The saved model contains the architecture, weights, and other necessary configurations. Saving a model is crucial for reusing it without the need for retraining. This can be beneficial for deploying the model in another environment, sharing it with others, or continuing training in the future. By saving the model in a file, it can be loaded back into the code using Keras models. Load_model, for making predictions or further training. A pre-trained Keras model stored in a file named my_Keras_model H5 can be loaded using the load_model function from Keras. This model could have been trained and saved beforehand for tasks like classification, regression, or other machine learning problems. Loading a pre-trained model allows making predictions on new data without retraining the entire model. This approach is beneficial when you have a trained model and need to use it for predictions on unseen data. This process involves invoking the predict method on a machine learning model with fresh data, x_new, to generate predictions. The model leverages the acquired patterns from the training data to forecast outcomes for the new input. In machine learning, post-training a model on a labeled dataset, it serves to forecast results for novel, undisclosed data. This forecasting stage is pivotal in machine learning workflows as it enables the utilization of the model in real-life scenarios to gain insights or make informed choices founded on the predictions. The predict method accepts the new data as input and yields projected outputs utilizing the learned model parameters. Saving the weights of a Keras model to a file named my_Keras_weights CKPT allows you to store the current state of the model for future use. This could include retraining the model, making predictions, or sharing it with others. By saving the weights separately from the model architecture, you can preserve only the learned parameters of the model, weights, without duplicating the entire model structure. This approach can be advantageous when aiming to save disk space and time by avoiding redundant storage of the model architecture. When you need to use the model later, you can reload these saved weights into the model to restore its previous state, weights. This is particularly useful when you have trained a model and wish to apply it for inference or fine-tuning without starting the training process from the beginning. This process loads pre-trained weights, parameters, saved in a file named my_keras_weights (ckpt) to a Keras model. Loading pre-trained weights is beneficial when you have a trained model that you wish to reuse for activities such as prediction, fine-tuning, or transfer learning on new or similar data. By loading the saved weights, you can skip the process of retraining the model from the beginning, thus saving time and computational resources. The load_weights function of the model object is utilized in this scenario to load the weights from the specified file and apply them to the model. This ensures that the model is initialized with the learned parameters acquired during training. In a machine learning or deep learning project using Keras with TensorFlow backend, the following steps are taken. 1. Clearing the Keras session using Keras. Backend. Clear_session helps release memory allocated for the TensorFlow graph efficiently. This is particularly useful when creating multiple models in a loop or as part of a function. 2. Setting the random seed for NumPy's random number generator with NP. Random seed 42 ensures reproducibility of results, generating the same set of random numbers each time the code is run. 3. Setting the random seed for TensorFlow's random number generator with TF. Random.set_seed 42 ensures consistency in results for operations relying on randomization, e.g., weight initialization in a neural network, whenever the code is executed. These functions are valuable for debugging, testing, and ensuring reproducibility in machine learning experiments involving random processes like weight initialization, data shuffling, dropout, among others. This text explains how a neural network model is created using the Keras library with multiple layers. The sequential model in Keras enables the creation of models layer by layer. In this scenario, a sequential model is formed with 3 layers. 1. The first layer is a dense layer with 30 neurons and ReLU activation, consuming input data of shape, 8. 2. The second layer is another dense layer with 30 neurons and ReLU activation. 3. The final layer is a dense layer with 1 neuron, often used for regression tasks requiring prediction of a single output value. Each dense layer represents a fully connected layer in the neural network. The number of neurons in each layer and the choice of activation function, such as ReLU, are adjustable hyperparameters that can enhance the model's performance. Neural networks are adept at recognizing intricate patterns in data and making predictions or classifications based on these patterns. This code outlines the architecture of a neural network model intended for training on a dataset to learn patterns and predict outcomes on new, unseen data. To summarize, this script defines a neural network model architecture with 3 dense layers for a regression task. Subsequently, the model can be compiled, trained, and assessed using appropriate data. This text outlines the process of training a Keras model using mean squared error, MSE, as the loss function and stochastic gradient descent, SGD, as the optimizer. It includes utilizing model checkpoints to save the best model during training based on validation data. The breakdown of the code is as follows. 1. Compiling the Keras model with MSE loss and SGD optimizer with a learning rate of 0.001. 2. Creating a callback that saves the best model during training as an HDF5 file named my_Keras_model H5. 3. Training the model for 10 epochs using X_train and Y_train data, validating on X_valid and Y_valid. Utilizing the model checkpoint callback to save the best model based on validation loss. 4. Loading the best model saved during training from the file my_Keras_model H5, based on validation performance. 5. Evaluating the loaded model on the test dataset using MSE as the metric. Utilizing model checkpoints is crucial in deep learning to prevent overfitting and maintain the best model based on validation performance. This allows for easy retrieval of the best model even if training continues, ensuring the model generalizes well to unseen data. This text describes the process of training a machine learning model using Keras. 1. The model is compiled using a specified loss function, MSE, for mean-squared error, and optimizer, stochastic gradient descent or SGD, with a learning rate of 1e3. 2. The early stopping callback is utilized to halt training when the monitored metric, validation loss, stops improving, helping prevent overfitting and save time by early stopping if the model converges. 3. The model is trained using the fit function with training data, x_train, y_train, for 100 epochs and validation data, x_valid, y_valid. 2 callbacks are included, checkpoint_CB and early_stopping_CB. 4. The evaluate function is employed to assess the model's performance on the test dataset, x_test, y_test, using mean-squared error as the loss function, providing the mean-squared error on the test data. In summary, this process sets up the model for training, implements monitoring and stopping mechanisms, conducts training, and evaluates the model's performance on an independent test set, aiding in the development and assessment of the model's generalization capabilities. This custom Keras callback, named print_val_train_ratio callback, is designed to print the ratio between the validation loss and the training loss at the end of each epoch during the training process. It accomplishes this by utilizing the on_epoch_end method from Keras callbacks, which is triggered by Keras at the conclusion of each epoch in the training phase, enabling the execution of customized actions. The printed ratio between validation loss and training loss offers insights into the model's generalization to unseen data in comparison to the data used for training. Monitoring this ratio aids in detecting overfitting or underfitting problems within the model. Leveraging custom callbacks in Keras is advantageous for overseeing and managing the training process, implementing personalized logic, and executing actions at specific stages during training. It provides flexibility and customization options beyond the standard functionalities of Keras. This particular callback is useful for monitoring the model's generalization performance throughout training. This text describes how a machine learning model is trained using the fit method from TensorFlow or Keras library. The model is trained for one epoch with training data x_train and y_train, along with validation data x_valid and y_valid. The callbacks parameter is utilized to define callback functions that run during training. The specific callback used here is print_val_train_ratio callback, which prints the ratio of validation loss to training loss at the end of each epoch. Callbacks are helpful for monitoring training, like saving the model, adjusting learning rates, or logging progress. The print_val_train_ratio callback provides insights into the relationship between training and validation loss, aiding in assessing model performance and potential overfitting. A root log directory path is created by combining the current directory with a folder named my_logs, using the os path join function. The main aim of this practice is to organize logs separately from other application files. This helps maintain a clean directory structure and simplifies the process of locating and managing logs for debugging, monitoring, or analysis. By utilizing this method, logs are stored in a specific folder for easier access and maintenance. The function get_run_logdir is defined to create a unique timestamp-based run id using the current date and time. It utilizes the stref_time function from the time module to format the timestamp as run_year_month_day hour_minute_second. Once the function is defined, it is called to generate a run log directory path under the root_logdir directory. The function then returns this formatted path. This code is beneficial when there is a need to create distinctive log directories or file names based on the current date and time. It aids in organizing and monitoring logs with timestamps for better differentiation and management. In machine learning projects, the following actions are commonly used with the Keras library on TensorFlow. 1. Clearing the Keras session using Keras. Backend. Clear_session removes all existing graph information in the TensorFlow backend. This is helpful when starting a new model or retraining an existing one without interference from previous models. 2. Setting the random seed for NumPy to 42 with NP. Random seed 42 ensures reproducibility in machine learning results. Using the same seed value allows for consistent random numbers when running code on the same hardware. 3. TF random.set_seed 42 sets the random seed for TensorFlow's random number generator to 42, ensuring consistent output for operations relying on random numbers. These commands are crucial for reproducibility and debugging in machine learning projects. They aid in identifying bugs, comparing models, and sharing results. By establishing fixed random seeds, one can ensure that their model's outcomes are reliable and reproducible by others. This neural network model is defined using Keras with 3 layers. The first 2 layers have 30 neurons each with the ReLU activation function, while the last layer has a single neuron for regression tasks. The model is compiled using mean-squared error loss and stochastic gradient descent optimizer with a learning rate of 0.001. Creating a neural network model for regression tasks involves using the sequential model, which adds layers in sequence. Compiling the model with a loss function and an optimizer is essential before training. The loss function evaluates the model's performance, and the optimizer updates the weights based on the loss function during training. The learning rate parameter of the optimizer controls the weight updates in each training step. Training a neural network model using TensorFlow Keras involves using various callbacks to enhance the training process. 1. TensorBoard callback. This callback creates a TensorBoard object to log training and validation metrics at a specified directory, enabling analysis of the model's performance using TensorBoard. 2. Fit method. This method trains the model on the training data for a specified number of epochs. Additionally, the validation_data parameter evaluates the model after each epoch to monitor its performance. Using callbacks like TensorBoard and model checkpoint provides insights into the model's performance, allowing for better decision-making and optimization during the training process. TensorBoard is a visualization tool that comes with TensorFlow, a popular machine learning framework. It enables users to visualize various aspects of their machine learning models, such as loss curves, accuracy metrics, and computational graphs. To use TensorBoard in a Jupyter notebook, you can load the extension with the %load_x TensorBoard magic command. Then, you can launch the TensorBoard server by running %TensorBoard, logdir equals my_logs. Port equals 6006, specifying the logs directory and the port number. This allows you to view the visualizations in a web browser. TensorBoard is valuable for gaining insights into the training process, monitoring metrics in real time, identifying issues with the model, and optimizing the model's performance. It helps users make informed decisions for improving accuracy and efficiency. This snippet is referencing a function called get_run_logdir, which is used to fetch a particular directory path associated with running logs. The returned run_logdir2 likely indicates the location where the logs are saved. There are several reasons for implementing this code. 1. Logging and debugging. **** The code may be utilized to handle and structure logs created while a program runs, for purposes such as debugging, error tracking, or monitoring. 2. Configurability. Having a dedicated function for obtaining the log directory enables easy modification or configuration of the path without the need to update multiple code references. 3. Consistency. Offering a standardized method for accessing log directories promotes uniformity and consistency in log management. 4. Security. It can aid in isolating logs from other system data or files, which can enhance security measures and access control. In practice, the get_run_logdir function might be designed to either dynamically create a new log directory based on real-time conditions or fetch a predefined log directory path according to specific criteria or configurations. When working with deep learning models in the Keras library with a TensorFlow backend, these steps are typically followed. 1. Clearing the current Keras session using Keras backend. Clear_session helps release memory and internal state from previous operations. This is useful when multiple models are created in the same script or notebook to prevent memory leaks. 2. Setting the random seed for NumPy random number generation to 42 with NP random seed 42 ensures result reproducibility and random number generation within the code. Consistent random numbers are generated every time the code is run with the same seed value. 3. Setting the random seed for TensorFlow random number generation to 42 by using tf random.set_seed 42 is similar to setting the seed for NumPy but is specific to TensorFlow. By setting seeds for both NumPy and TensorFlow, randomness in deep learning models and experiments is controlled, making the results reproducible. This text describes the creation of a neural network model using the Keras library. The model consists of 3 layers, 2 hidden layers with 30 neurons each and ReLU activation function, and 1 output layer with a single neuron for regression task. After defining the model, it is compiled with mean-squared error, MSE, loss function and stochastic gradient descent (SGD) optimizer with a learning rate of 0.05. This setup ensures that during training, the model minimizes the MSE between predicted values and actual target values using stochastic gradient descent. Setting up the architecture and training configuration of the neural network model is crucial before initiating the training process. Decisions regarding the model structure, loss function, and optimizer can greatly influence the performance and efficiency of the neural network in a specific task. Training a neural network model using TensorFlow Keras involves the following steps and purposes. 1. TensorBoard_CB. It produces a TensorBoard callback object which records training and validation metrics during model training. TensorBoard allows for performance monitoring, internal states inspection, and issue debugging. 2. History equals model.fit. This line initiates the model training process. The model is trained on training data x_train and y_train for 30 epochs, with validation occurring on validation data x_valid and y_valid. 3. Callbacks equals checkpoint_CB TensorBoard_CB. 2 callbacks are applied during training. Checkpoint_CB and TensorBoard_CB. Checkpoint_CB saves the model's weights during training, while TensorBoard_CB logs training and validation metrics for visualization in TensorBoard later on. Utilizing these callbacks and training aids in recording model progress, hyperparameter tuning, performance metric analysis, and enhancing the neural network architecture for improved outcomes. The Keras TensorBoard callback facilitates visualizing a model's training progress and performance using the TensorBoard tool from the TensorFlow library. With this callback, you can customize logging options for tracking training and validation metrics like loss and accuracy, visualize model architectures, and monitor various aspects during training. The TensorBoard callback collects data, such as loss and accuracy metrics, from the model while training and stores this information in log files that TensorBoard can interpret and present in a user-friendly format. This feature enables real-time monitoring of the model's training, performance analysis, and informed decisions on optimizations. When training deep learning models, utilizing the TensorBoard callback is crucial. It offers insights into the training process and aids in refining the model's architecture and hyperparameters for improved results. In a machine learning project utilizing Keras with TensorFlow backend, the following actions are explained. 1. Clearing the Keras session using Keras. Backend. Clear_session. This operation clears the Keras session, which stores the model's components. Clearing the session prevents clutter from previous models and aids in maintaining a clean slate for training new models. 2. Setting the random seed to 42 for NumPy with NP. Random. Seed, 42. This line ensures reproducibility in data handling and generation. Consistent results are produced when the code is run using the same random seed, which is crucial for debugging and comparing model performance. 3. Setting the random seed to 42 for TensorFlow with TF. Random.set_seed, 42. Similar to NumPy, setting the random seed in TensorFlow guarantees reproducibility in operations involving randomness, such as weight initialization and data shuffling. These practices are vital in machine learning to meet requirements for reproducibility and consistency. By establishing random seeds and clearing the session, experiments remain reproducible and are shielded from interference caused by previous models or random initialization. The function, build_model, constructs a neural network model using the Keras library. It takes 4 hyperparameters as inputs: n_hidden, n_neurons, learning_rate, and input_shape. Here's an overview of what the function does. 1. It creates a sequential model object from Keras. 2. Sets the input shape for the model based on the input_shape parameter. 3. Adds n_hidden layers to the model. Each hidden layer is a dense layer with n_neurons and ReLU activation. 4. Adds an output layer with a single neuron and no activation function. 5. Configures the model for training with mean squared error, MSE, as the loss function and stochastic gradient descent, SGD, optimizer using the specified learning rate. 6. Finally, it returns the compiled model. This function is convenient for building neural network models with adjustable architecture and hyperparameters for regression tasks. By providing the hyperparameters to this function, you can easily create and compile a neural network model tailored to your specific requirements without rewriting the model creation and compilation code. This text describes how to create a scikit-learn compatible wrapper for a Keras neural network model. The wrapper enables the use of Keras models within the scikit-learn framework. This allows the model to benefit from scikit-learn's tools like grid search CV for tasks such as hyperparameter tuning and cross-validation. The code includes a Keras regressor wrapper designed for regression tasks. It requires a build_model function as an argument, which defines and returns the Keras model architecture. The Keras regressor then adapts this model for compatibility with scikit-learn. By implementing this approach, users can combine the deep learning capabilities of Keras with the versatile tools of scikit-learn to efficiently build and train neural network models for regression tasks. This text explains how to train a regression model using the Keras library. The line keras_reg.fit, x_train, y_train, epochs equals 100, fits the regression model keras_reg to the training data x_train with corresponding target values y_train over 100 epochs. This repetitive process aims to help the model learn the underlying patterns in the data. Validation_data equals X_valid, Y_valid, specifies the validation data to evaluate model performance during training. X_valid represents validation input data and Y_valid is the corresponding target data. Callbacks equals Keras. Callbacks. Early stopping, patience equals 10, implements early stopping during training. The early stopping callback tracks a specified metric, e.g., validation loss, and halts training if the metric's improvement stagnates after a defined number of epochs, controlled by the patience parameter, set to 10 here. Early stopping aids in curbing overfitting and conserving computational resources by promptly stopping training when the model no longer improves on the validation set. Ensuring the effective training of the regression model involves applying this code to monitor performance and prevent overfitting using early stopping techniques. The mean squared error, MSE, of a regression model is being calculated using the model's score function with test features, x_test, and target values, y_test. MSE is a common metric for evaluating regression model performance by measuring the average of squared differences between actual and predicted values. A lower MSE indicates a better model fit. In this case, Keras_reg is presumed to be an instance of a regression model created with Keras, a popular neural network library in Python. The score function in Keras likely computes the mean squared error for regression models on provided test data. Calculating MSE on test data assists in evaluating the model's ability to generalize and make accurate predictions on new data. Evaluating the model on a separate test dataset provides a reliable estimation of its performance on unseen data. A trained Keras regression model, Keras_reg, is used to make predictions on new data, x_new. The predict method takes the new input data as its argument and utilizes the trained model to forecast the output values based on learned patterns and relationships in the data. This process is crucial in machine learning workflows for applying a trained model to new, unseen data to generate predictions. Utilizing this code enables us to acquire predictions from the regression model for the new input data. Setting the random seed for both NumPy and TensorFlow libraries ensures that the randomly generated numbers are consistent each time the code is run. This helps in obtaining reproducible results when working with random elements in machine learning models or experiments. A seed of 42 is set in this case for both the NumPy and TensorFlow libraries. This guarantees that the random numbers produced by these libraries will remain the same every time the code is executed. Such consistency is helpful for debugging issues or comparing results across multiple runs of the code. This snippet performs hyperparameter tuning for a Keras model using randomized search cross-validation. Here is an overview of each component. 1. SciPy. Stats. Reciprocal. Utilized to sample hyperparameters from a reciprocal distribution. Specifically, it is used to sample learning rates between 3e4 and 3e2. 2. Sklearn. Model_selection. Randomized search CV. This class conducts a random search for hyperparameters for an estimator. It fits the model multiple times with different parameter settings and cross-validates the outcomes. 3. Param_distribs. A dictionary containing the hyperparameters to be explored during the random search. For example, n_hidden, from 0, 1, 2, or 3, n_neurons, from 1 to 99, and learning_rate, from the reciprocal distribution. 4. n_iter. Specifies the number of sampled parameter settings during the search. 5. CV. specifies the number of cross-validation folds to utilize during the search. 6. Verbose controls the level of output verbosity. 7. rnd_search_cv.fit. This method fits the randomized search on the provided data, exploring various hyperparameter combinations for the given iterations and returning the best parameters discovered. Utilizing this code is essential for selecting optimal hyperparameters for machine learning models. Hyperparameter tuning is crucial for enhancing model performance, and tools like randomized search cross-validation streamline the process of exploring a broad range of hyperparameters to identify the best combination for the dataset. This text likely describes the retrieval of the best parameters found by a randomized search cross-validation, randomized search CV process. Randomized search CV is an optimization technique used to fine-tune hyperparameters of a machine learning model. It involves searching through a specified set of hyperparameters randomly, conducting cross-validation to assess the model's performance with each parameter set, and ultimately identifying the best set of hyperparameters that yielded the highest performance. Accessing rnd_search_cv best_params_ allows retrieval of the best hyperparameters discovered during the randomized search process. These optimal settings can then be utilized to train the final model, leading to enhanced performance and generalization of the machine learning model. The best score achieved during a randomized search cross-validation process can be obtained. In machine learning, adjusting the hyperparameters of a model is essential to find the most effective combination for optimal performance. Randomized search cross-validation is a method used to efficiently explore a defined set of hyperparameters. The best_score_ attribute provides the average cross-validated score of the best estimator discovered in the search process. This assists in recognizing the top model according to the designated scoring metric. The randomized search CV algorithm is employed to identify the best estimator model. This technique fine-tunes the hyperparameters of a machine learning model by randomly selecting combinations from a defined search space and evaluating their performance through cross-validation. The best combination of hyperparameters that yields the highest performance metric is chosen as the best estimator. Accessing rnd_search_cv best_estimator_ allows retrieval of the optimal model with the best hyperparameters identified during the randomized search process. This best estimator can be utilized for predicting on new data or conducting additional analysis. This text explains the process of calculating the score of a machine learning model using the test set data and a randomized search CV object for hyperparameter tuning. The score indicates how well the model performs on unseen data, emphasizing the importance of evaluating model performance on the test set to avoid overfitting. By assessing the model's performance objectively, adjustments or improvements can be made if needed. The objective of this snippet is to retrieve the best estimator model from a randomized search CV object. Randomized search CV is used to explore the optimal hyperparameters of a machine learning model by randomly choosing from a specified parameter grid. Once the randomized search CV object has been trained on the data, the best estimator model can be accessed through the best_estimator_ attribute. In this instance, the intention is to obtain the model of the finest estimator from the randomized search CV object to use it for generating predictions. Utilizing randomized search CV enables us to efficiently navigate a defined hyperparameter space and identify the most suitable combination of hyperparameters for our machine learning model. This process has the potential to enhance the overall performance of the model. This snippet is designed to assess the performance of a machine learning model using test data x_test and their corresponding labels y_test. The evaluate function computes metrics like accuracy, loss, precision, recall, and F1 score based on the model's predictions on the test data. Evaluation is essential for understanding how well the trained model generalizes to new data. By comparing the model's predictions with the actual labels in the test set, we can determine its accuracy and identify potential issues such as overfitting or underfitting. This evaluation helps in making informed decisions about model refinement, feature engineering, or additional training to enhance the model's performance before deploying it in real-world applications. This text discusses loading the MNIST dataset using TensorFlow's Keras library. The MNIST dataset is well known in machine learning and consists of images with handwritten digits, 0 to 9. By utilizing Keras datasets MNIST load_data, the dataset is split into training and testing sets, containing features and labels. The training data, x_train_full, y_train_full, is used for model training, while the testing data, x_test, y_test, assesses the model's performance. Loading the MNIST dataset is significant for establishing a standardized dataset to create and test machine learning models, particularly for tasks like image classification. Accessing this dataset enables the development and training of models without manual data preprocessing or collection, aiding in focusing on model design and training, essential for crafting precise and effective machine learning models. The shape of the dataset named x_train_full can be obtained using the shape attribute in NumPy arrays and many other Python packages. For a two-dimensional array, such as one representing a dataset, shape provides a tuple with two elements. The first element indicates the number of rows, samples, and the second element indicates the number of columns, features. Understanding the shape of a dataset is essential for data analysis and machine learning as it reveals the dataset's size, the available features, and aids in identifying and rectifying dimension-related issues in the code. The command x_train_full dtype helps identify the data type of the elements in the variable x_train_full. This is essential as different machine learning algorithms and mathematical operations require specific data types like integers, floating point numbers, or strings to function effectively. Checking the data type of the elements in a variable ensures the data is in the right format for the task. For instance, when dealing with numerical data, the expected data types are usually integers or floating point numbers. If the data type is incorrect, it might be necessary to convert or normalize the data before continuing with analysis or modeling. This process preprocesses data for a machine learning model that involves image data. Here's a breakdown of what it does. 1. It divides the training data x_train_full into two portions, x_valid and x_train. The first 5,000 samples are allocated for validation, x_valid, while the remaining samples are for training, x_train. 2. A similar split is performed for the corresponding targets y_train_full to yield y_valid and y_train. 3. It normalizes the pixel values of the images in x_valid, x_train, and x_test by dividing them by 255. Normalizing the pixel values to a range between 0 and 1 is crucial for neural networks as it enhances training and potentially accelerates convergence. In essence, this approach readies the image data for the neural network model by segregating it into training and validation sets and standardizing the pixel values. These preprocessing steps enhance the training process and improve the overall performance of the model. The matplotlib library is used to display an image from the training data, x_train, at index 0. Explanation. 1. Displaying the image from x_train, 0. Using a binary color map with plt. imshow. This command shows the image located at index 0 of the x_train dataset in black and white using a binary color map. The imshow function is utilized to display the image in the plot. 2. Turning off axis lines and labels with plt. Axis, off. This statement hides the axis lines and labels in the plot, allowing only the image to be displayed without any additional information such as axes. 3. Showing the plot with plt. Show. This instruction presents the plot with the image based on the settings defined by the previous commands. This code is useful for visualizing dataset images to gain insights into the data, assess image quality, or verify data preprocessing steps. It can also aid in debugging by ensuring correct image loading and examining specific dataset images. In the context of machine learning, y_train usually represents the training labels. During supervised machine learning, data is commonly split into features, input, and labels, output. The y_train array typically stores the output values, labels, for the training data. In a standard machine learning workflow, y_train is used to train the model so that it can recognize patterns in the input data, x_train, along with their corresponding outputs. This training is vital for the model to accurately predict outputs when provided with new, unseen data. Therefore, y_train plays a significant role in training a machine learning model as it supplies the correct answers needed for the model to learn during the training phase. It is a fundamental component of supervised learning, guaranteeing that the model enhances its predictive capabilities. Accessing the shape attribute of the variable called x_valid provides information about the dimensions of the array or dataset represented by the variable. Analyzing the structure of the data in the x_valid variable is crucial for data manipulation and analysis. Knowing the shape of the data is helpful in determining the appropriate ways to process or analyze it efficiently. The x_test shape command is utilized to access the dimensions, shape, of the variable x_test. In the context of machine learning, x_test typically denotes the features of the test dataset that will be input into a trained model for prediction or testing purposes. The shape attribute returns a tuple that describes the object's dimensions. For instance, for a two-dimensional array or data frame, the shape will be specified as number of rows, number of columns. By examining the shape of x_test, we can verify that the test dataset contains the expected number of samples and features. This validation step is crucial before using a machine learning model for predictions because the input data must conform to the correct shape for the model to process it accurately. This snippet creates a grid of subplots to show images and labels. The number of rows and columns in the grid is determined by n_rows and n_calls. For each image in x_train, the code calculates the index of the current subplot based on its position in the grid. It then positions the subplot using PLT. Subplot displays the image with PLT. IMShow sets the label as the subplot title, and turns off the axes using PLT. Axis off, PLT. Subplots _adjust adjusts the spacing between subplots, and PLT. Show displays the grid. This code enables visualization of many images with labels in an organized grid, facilitating dataset analysis and pattern recognition. Matplotlib library is used for creating and displaying the grid, providing a convenient way to inspect image data. This text discusses a custom callback class called exponential learning rate in Keras for adjusting the learning rate exponentially during training. The exponential learning rate class is initialized with a factor parameter that determines the adjustment of the learning rate after each batch. During training, the on_batch_end method records the current learning rate and loss, updates the optimizer's learning rate by multiplying it with the factor, allowing for dynamic adjustments based on the defined factor. This flexibility can improve convergence and handle specific training scenarios. Custom callbacks like exponential learning rate offer the ability to adapt the training process, fine-tune learning rate schedules, and add functionalities not available in Keras built-in callbacks. In a deep learning project using the Keras library, it is helpful to include the following operations. 1. Clearing the Keras session with Keras. Backend. Clear_session, releases internal variables and frees memory. This prevents clutter in memory when working on multiple models within the same script or notebook. 2. Setting the NumPy random seed to 42 with NP. Random seed 42 ensures reproducibility in the code. This means that the same random numbers will be generated each time the code is run, aiding in debugging and model performance comparison. 3. Using TF. Random.set_seed 42 sets the TensorFlow random seed to 42, ensuring consistent results for operations relying on randomness in TensorFlow. These functions help maintain reproducibility and facilitate debugging in deep learning projects. Reproducibility is key to ensuring consistent model behavior and can assist in troubleshooting unexpected issues. This text describes using the Keras library to define a neural network model for image classification. 1. Sequential model. This creates a sequential model, which is a linear stack of layers. This enables building neural networks by adding layers one by one. 2. Flatten layer. This layer transforms input images from a 2D array, 28 by 28 pixels, into a 1D array, 784 pixels, to input into the neural network. 3. Dense layer, 300 neurons. This adds a fully connected layer with 300 neurons using the ReLU activation function. 4. Dense layer, 100 neurons. This adds another fully connected layer with 100 neurons using the ReLU activation function. 5. Output layer, 10 neurons. This adds the output layer with 10 neurons, one for each class in the dataset, using the softmax activation function to output probability scores for each class. Creating layers, specifying the number of neurons, and activation functions are essential in defining the architecture of neural networks. The sequential model simplifies this process by allowing stacking layers one after the other, making it a popular method in building deep learning models due to its simplicity and effectiveness. Setting up the configuration for training a neural network model using the Keras deep learning library entails several key steps. 1. The model is compiled to prepare it for training. The loss function, in this case sparse categorical cross-entropy, measures the model's performance. The optimizer, stochastic gradient descent, SGD, with a learning rate of 0.001, updates the weights to minimize the loss. The evaluation metric, accuracy, monitors the fraction of correctly classified items. 2. An exponential learning rate instance called expon_LR is created to manage the learning rate during training. This custom scheduler adjusts the learning rate exponentially, with the factor equals 1.005 specifying the rate of increase or decrease after each epoch. Configuring these aspects, including the loss function, optimizer, metrics, and learning rate scheduler, is crucial for effectively training a neural network. These choices significantly influence the model's convergence and performance. Properly setting these parameters can enhance the efficiency of the training process and the neural network's overall performance. This text describes the process of training a TensorFlow or Keras model using the FIT method. The model is trained on a training dataset, x_train, y_train, for one epoch, while also evaluating its performance on a validation dataset, x_valid, y_valid. The callbacks parameter is used to incorporate additional functionality during training, with the mention of the exponent_lr callback in this scenario. The exponent_lr callback is a custom object designed to adjust the learning rate using an exponential decay strategy. Callbacks can be employed to customize the training process by enabling tasks such as saving model checkpoints, implementing early stopping, or dynamically modifying hyperparameters like the learning rate. In this specific case, the exponent_lr callback is likely being used to control the learning rate schedule during training to potentially enhance the model's performance or convergence speed. This text provides a description of a data visualization task involving the use of Python's matplotlib library. 1. It generates a line plot to illustrate the connection between learning rates, exponent_lr rates, and their corresponding losses, exponent_lr losses. 2. The x-axis scale is set to logarithmic using plt.gca.set_xscale log, for cases where the data covers multiple orders of magnitude. 3. A horizontal line is incorporated into the plot to indicate the minimum loss value in the dataset through plt h-lines. 4. The plot's axis limits are adjusted with plt axis to ensure all data points are visible. The x-axis range is determined by the minimum and maximum learning rates, while the y-axis range starts from 0 up to the first loss value. 5. To improve readability, a grid is added to the plot using plt grid. 6. The x-axis and y-axis are labeled as learning rate and loss, respectively, using plt xlabel and plt ylabel. This code aids in examining the relationship between learning rates and losses in a machine learning model, particularly when evaluating a learning rate finder's behavior or fine-tuning hyperparameters during model training. The logarithmic scale on the x-axis facilitates the observation of data patterns across a wide value range. This snippet describes the following actions. 1. Keras backend clear_session clears the current Keras session to free up memory and create a fresh session for building new models without any remnants of previous ones. 2. NP random seed 42 sets the seed for NumPy's random number generator to ensure reproducible random numbers across different runs. 3. TF random.set_seed 42 sets the seed for TensorFlow's random number generator to maintain reproducibility in TensorFlow operations involving randomness. Setting seeds for random number generators is crucial in machine learning to achieve reproducible results. By clearing the Keras session and setting seeds for both NumPy and TensorFlow generators, a consistent environment is created for model training and evaluation. This consistency facilitates debugging, result comparison, and sharing findings with others. This text describes the architecture of a neural network model created using the Keras Sequential API. The neural network consists of multiple layers. 1. The first layer is a flattened layer that converts the input 2D array 28 by 28 pixels, into a 1D array, 784 pixels, to prepare the data for the subsequent dense layers. 2. The second layer is a dense layer with 300 neurons and ReLU activation function. It applies weights to the data and introduces non-linearity with the ReLU function. 3. The third layer is another dense layer with 100 neurons and ReLU activation function, adding further weights and non-linearity to the input. 4. The final layer is a dense layer with 10 neurons and the softmax activation function. This layer serves as the output layer, presenting the class probabilities for the classification task. Softmax ensures output values are between 0 and 1, summing up to 1 for class probabilities. By stacking these layers in a sequential model, a feedforward neural network for classification tasks is created. The flattened layer preprocesses the input data for the dense layers, which are standard neural network layers with connections between every neuron in adjacent layers. Activation functions such as ReLU bring non-linearity, while softmax in the output layer converts scores into class probabilities. Defining this architecture is crucial before training the neural network on datasets like image recognition or classification tasks. This configuration sets up the training process for a neural network using the Keras library. Here's a summary. 1. Loss function * specifies sparse categorical crossentropy, a common choice for multi-class classification with integer labels. 2. Optimizer * utilizes stochastic gradient descent (SGD) with a learning rate of 0.3 to update the neural network's weights based on loss gradients. 3. Metrics * monitors accuracy during training to assess model performance based on correctly classified samples. Configuring these settings prepares the model for training by defining the loss function, optimizer, and metrics. These choices are critical in determining how the model learns and evaluates its performance, impacting the training process and final model quality. This snippet initializes a variable run_index with the value 1 and constructs a log directory path using os path join. The log directory path is based on the current working directory, os curter, with a subdirectory structure like my_MNIST_logs, run_o3d. The o3d formatting ensures the run_index is padded with zeros to a length of 3 digits. This code helps in creating a dynamic log directory path for logging purposes in projects, model training, or other tasks. The run_index uniquely identifies each run or iteration, ensuring log files from different runs are stored in separate directories. Such dynamic directory creation is commonly used in machine learning projects, experiments tracking, or application logs to organize and store logs for easy retrieval and analysis. This text discusses the usage of different callback functions in a Keras model training process. 1. Early stopping * monitors a specific metric during training and halts the process early if the metric's improvement stalls, based on a set, patience, parameter. This helps prevent overfitting and unnecessary computations. 2. Model checkpoint * saves the model after each epoch if its performance on a validation set is the best seen so far. This ensures you retain the best model and progress in case of interruptions. 3. TensorBoard * writes logs for TensorBoard, a visualization tool for monitoring and analyzing the model's performance. This tool enables visualizations of metrics such as loss and accuracy. By employing these callback functions, the training process can be enhanced by preventing overfitting through early stopping, preserving the best model checkpoint for future use, and gaining insights into training progress through TensorBoard visualizations. To reload a saved model from a file named my_MNIST_model H5, using Keras, the following steps are taken. The model is then evaluated using test data, x_test, y_test, to assess performance metrics like accuracy and loss. Reloading a model from a saved file is essential for utilizing a trained model in prediction or evaluation without the need for retraining. This approach enables the model to be saved after training, allowing for its reuse without the requirement to undergo training repetitively. This is particularly significant when handling deep learning models on extensive datasets, as training can be both time and resource consuming. Launching a TensorBoard server allows for visualization of training logs. TensorBoard is a tool in TensorFlow that displays metrics such as loss and accuracy, along with the model's graph structure. Here is a breakdown of the command. Running %TensorBoard initiates the TensorBoard magic command in Jupyter Notebooks or Google Colab. Logdir equals my_MNIST_logs designates the log directory for visualization, using logs from my_MNIST_logs. Port equals 6006 inches specifies the port number for TensorBoard to run, typically set at 6006 by default. Running this command enables visualization of training progress and model performance, aiding in understanding the model's behavior, issue identification, and performance optimization.